Welcome to Science, to Sleep By. Tonight, let's take a gentle journey through time and space. As you settle in, close your eyes, and let your mind drift. We'll explore one of the greatest mysteries of the cosmos, the Big Bang. Was it really the beginning of everything? Or just one chapter in a story far older than we can imagine? Together, we'll let science guide us, softly, carefully, and with wonder. When we talk about the Big Bang, we're not speaking of an ordinary explosion like fireworks in the sky or the blast of dynamite echoing in a canyon. The Big Bang is something far more profound, far more mysterious, and far more delicate in its description. Imagine a universe that did not yet exist. No space stretching endlessly, no stars twinkling, no galaxies swirling in their graceful spirals. Not even silence, because even silence needs space to echo through. The Big Bang, as scientists describe it, was the moment when everything that we know, everything that we see, and everything that we are made of began from a state so small, so dense, and so hot that our minds can barely wrap around it. For decades, astronomers and physicists have traced back the history of the cosmos like detectives uncovering clues at the scene of a great mystery. What they found is that the universe is not static. It is not sitting still like a painting hung on the wall of time. Instead, it is expanding, stretching outward in every direction. The galaxies are not fixed in place. They are drifting apart, carried along by the very fabric of space itself. This realization was first uncovered in the early 20th century, when Edwin Hubble looked through his telescope and saw that distant galaxies were moving away from us. Their light stretched into longer, redder wavelengths by the expansion of space. It was as though the entire universe was breathing out, releasing something that had once been compressed. Tracing that expansion backward, scientists asked a simple but staggering question. If everything is moving apart now, was there a time when everything was closer together? And if so, how close? How dense? How hot? The answer was almost unimaginable. There must have been a moment, about 13.8 billion years ago, when all of the energy, all of the matter, all of the laws of physics we know, were compressed into a single, tiny state. Not even the size of a star, or a planet, or a grain of sand. Smaller than an atom, smaller than anything our eyes or instruments can directly see. A singularity, a point where the equations break down, where time and space, as we understand them, seemed to dissolve, and then, in an instant, it expanded. Not into a pre-existing void, not into an empty room waiting to be filled, but into itself. The very act of expansion created the space in which the universe could exist. The Big Bang was not an explosion in space. It was the expansion of space. It was not fragments flying apart into an already existing emptiness. It was emptiness itself, being born, stretched, and filled with energy and matter. Scientists describe this beginning not with the noise and fire that the word bang suggests, but with the quiet mathematics of physics. Temperatures soared to unimaginable levels, trillions of degrees, hotter than the core of any star. In those first fractions of a second, particles flickered into existence, collided, and annihilated one another in a cosmic dance. Quarks, the building blocks of protons and neutrons, swirled in a hot soup. Energy condensed into matter, and matter dissolved back into energy, in a cycle so rapid and so intense, it defies intuition. As the universe expanded, it cooled. Though, cooling, here is a relative word. From unimaginably hot, it became merely extremely hot. In the first few minutes, the first atomic nuclei began to form. Hydrogen and helium, the simplest and lightest elements, fused out of the energy of the early fireball. These were the seeds, the foundation stones, for every star that would ever shine and every planet that would ever circle those stars. But the story of the Big Bang is not just about the matter that formed. It is about the very stage on which all of existence plays out, time and space themselves. When we say the universe began 13.8 billion years ago, we are not just saying that stars and galaxies began then. We are saying that time itself had a starting point. Before the Big Bang, There was no before in any conventional sense, because there was no time in which before could exist. The ticking of seconds, the flowing of moments, the very rhythm by which we measure life and change, all of it began in that singular instant. That is one of the most difficult and most awe-inspiring aspects of the Big Bang concept. Our everyday experience teaches us that everything has a cause, everything comes from something else, and everything unfolds in time. A tree grows from a seed, a river flows from a spring, a star forms from a cloud of gas. But the universe itself, where did it come from? What was its cause? If time began with the Big Bang, then asking what happened before the Big Bang may be as meaningless as asking what is north of the North Pole. This is not just a philosophical puzzle, it is a scientific frontier. Physicists continue to search for clues in the faint glow of ancient light, the cosmic microwave background, which carries the imprint of the universe's earliest moments. They use equations of general relativity and quantum mechanics to push back as far as they can, to model what conditions must have been like in those first trillionths of a second. Yet even the most advanced theories still stumble at the singularity. That point remains shrouded in mystery, a veil we cannot yet pierce. Still, the Big Bang concept remains one of the most successful frameworks in all of science. It explains why galaxies are receding from one another, why the universe is filled with the faint background radiation left over from its hot beginning, and why the simplest elements appear in the proportions that they do. It ties together observation, theory, and mathematics into a single grand narrative of cosmic origin. And though it does not tell us why there is something rather than nothing, it does describe, with remarkable precision, how the something we see today emerged from that primeval state. To sit with this idea is to feel the scale of the cosmos in a way that is both humbling and comforting. Every star, every planet, every cell in your body traces its history back to that single moment. The iron in your blood was forged in ancient stars, but the hydrogen atoms that fill your lungs with each breath were born in the first few minutes after the Big Bang. The same event that set galaxies spinning also set in motion the long chain of cause and effect that eventually led to you lying quietly tonight, listening to the story of the universe's birth. The Big Bang concept is not the end of inquiry. It is the beginning of curiosity. It opens doors rather than closing them, reminding us that the universe is not only stranger than we imagine, but stranger than we can imagine. And yet, even in that strangeness, there is a sense of belonging, a sense that we are participants in a cosmic story that began long ago, when space itself unfolded from a single, blazing point. If the Big Bang was the opening note of the universe, then the cosmic background radiation is the faint echo of that note still ringing through the halls of space. It is often called the afterglow of creation, though it is not a bright light we can see with our eyes. Instead, it is a soft whisper of heat, stretched into microwaves by the expansion of the universe, bathing everything in a nearly uniform glow. It fills the cosmos from edge to edge, a silent and constant reminder of a beginning that once blazed with unimaginable fire. To understand why this radiation matters, we need to step back and picture the universe not as it is now, filled with galaxies and stars, but as it was when it was very young. In the first few 100,000 years after the Big Bang, the universe was not transparent. It was dense and hot, so much so that atoms could not yet exist in stable form. Instead, matter was in the form of plasma, a thick soup of protons, electrons, and photons, all colliding, scattering, and exchanging energy in an endless dance. Photons, the particles of light, could not travel freely through this plasma because they were constantly bouncing off free electrons. The universe was like a fog too thick to see through. It was glowing with light, but that light was trapped, unable to travel far without scattering. As the universe expanded, it cooled. And around 380,000 years after the Big Bang, something remarkable happened. The temperature dropped low enough for protons and electrons to combine and form the first neutral atoms. This event is called recombination. With electrons now bound into atoms, photons no longer scattered as frequently. The fog lifted. For the first time, light could travel freely across space. Those very first photons, released from the cosmic fog, are still traveling today. They have stretched and cooled over billions of years, becoming the faint microwave glow we detect as the cosmic background radiation. When astronomers first pointed their instruments to the sky and measured this radiation, they found it everywhere, in every direction. No matter where they looked, the signal was nearly the same. This was one of the strongest pieces of evidence that the universe really did begin in a hot, dense state. It was the lingering warmth of the Big Bang itself, now chilled to just 2.7 degrees above absolute zero, but still present, still detectable. Like embers that never quite go out, the discovery of this radiation was almost accidental. In the 1960s, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were trying to tune a radio antenna for satellite communications. No matter how they adjusted their equipment, they kept picking up a faint, persistent hiss. They thought it might be interference from New York City, or maybe droppings from pigeons roosting in the antenna. They cleaned it, they recalibrated, but the signal remained. Eventually, they realized what they were hearing was not local noise at all. It was the echo of the universe's birth. Without intending to, they had discovered the cosmic microwave background radiation. For this, they were awarded the Nobel Prize. But more importantly, their discovery confirmed one of the boldest predictions of the Big Bang Theory. This background radiation is not uniform in the most precise sense. With modern instruments like the COBE, WUMUP, and Planck satellites, scientists have mapped tiny variations in the temperature of this cosmic glow differences of only 1 part in 100,000. These subtle fluctuations are not random noise. They are the fingerprints of the early universe, showing where matter was slightly denser or thinner. Over billions of years, those tiny ripples of density became the vast cosmic structures we see today: galaxies, clusters of galaxies, and immense filaments stretching across the universe like a web. In this sense, the cosmic background radiation is like a baby picture of the universe. By studying it, scientists can glimpse what the cosmos looked like in its infancy. Long before stars or planets had formed, the uniformity of this radiation also tells us something extraordinary about the nature of the universe. Light can only travel so far in a given time. In the early universe, there were regions so far apart that, by all normal expectations, they could never have communicated with one another. Yet, when we look at the cosmic background radiation, those regions appear to have almost exactly the same temperature. How could different parts of the universe, separated by vast distances, have come into such perfect balance? This puzzle is known as the horizon problem, and it gave rise to the idea of cosmic inflation, a period of extremely rapid expansion in the first fractions of a second. After the Big Bang, inflation would have allowed different regions to start close enough together to share information, and even out their temperatures before being stretched apart by expansion. The background radiation, in its astonishing uniformity, whispers the story of inflation to us across billions of years. For us today, the cosmic background radiation might seem distant, almost irrelevant, because it is invisible to our senses. We cannot feel it on our skin or see it with our eyes. And yet, it is everywhere, all around us, all the time. If your television once displayed static when it lost a signal, a tiny fraction of that static was caused by cosmic background radiation. Every time you look into the night sky, whether you realize it or not, you are bathing in the ancient light of the universe's beginning. This radiation also serves as a bridge between science and wonder. On one hand, it is hard data, measured with exquisite precision, confirming equations and models about how the universe began. On the other hand, it is a kind of poetry in physics, the lingering glow of creation still warming the cosmos, still connecting us to a moment almost 14 billion years in the past. Imagine holding something that has traveled across nearly the entire history of time, unbroken, uninterrupted, a signal that began before the Earth existed, before the sun was born, before galaxies took shape. That is what cosmic background radiation is. It is not just light. It is memory, woven into the very fabric of the universe. As scientists continue to study it, the radiation continues to reveal secrets. It tells us about the density of the universe, the balance between matter and energy, and even about the mysterious presence of dark matter and dark energy. It acts like a cosmic code, one we are still learning to decipher. Each measurement sharpens the picture, each detail deepens our understanding. But even without all the equations, there is something deeply human in the thought that the universe carries with it a record of its birth. A whisper that has survived across unimaginable time, waiting for beings like us to notice and listen. When we think about beginnings, we usually imagine them happening within time. A day begins when the sun rises. A story begins with the first word on the page. A life begins with the first breath. But when we turn to the origin of the universe, the idea of beginnings takes on a much stranger shape, one that stretches our imagination beyond familiar ground. The Big Bang, as described by cosmology, was not just the beginning of matter, not just the beginning of stars and galaxies, but the beginning of time itself, the beginning of space itself. This is one of the most profound and difficult concepts in all of science, because it asks us to picture a moment when the very stage upon which everything unfolds, the stage of time and space, suddenly came into being. Imagine holding a clock in your hand. You can watch the seconds tick by, one after another, a steady rhythm that feels as real and certain as anything in life. But what if that clock had no first tick? What if the hands only started moving after the universe itself was born? According to the Big Bang model, that is exactly what happened. Time, the flow of moments, did not stretch backward infinitely. It began with the birth of the universe, roughly 13.8 billion years ago. Before that moment, asking what came before may not make sense, because before is a concept that depends on time already existing. This idea can be unsettling, because it cuts against our ordinary way of thinking. Our minds are used to cause and effect, to every event having something that preceded it. A fire begins when a match is struck. A wave begins when the wind pushes against the sea. But what caused the first instant of the universe? If time itself began with the Big Bang, there was no before in which a cause could exist. In this way, the question itself dissolves. It is as though we are standing at the North Pole and someone asks us to walk farther north. The request sounds logical at first, but when you think about it, there is no such thing as farther north. You are already at the limit. In a similar way, time seems to have a limit at its beginning, a point beyond which the word earlier has no meaning. The birth of space is equally profound. When we look around, space feels infinite and empty, a vast container into which planets, stars, and galaxies are placed. But the Big Bang tells us that space itself was created in that first moment. It is not a container waiting to be filled. It is part of the unfolding process of the universe itself. When the Big Bang occurred, it was not an explosion inside space. It was the expansion of space itself. Every atom, every particle, every photon of light was carried outward on the stretching fabric of the cosmos. Even today, galaxies are not flying apart into some pre-existing void. The void is expanding with them. To picture this, scientists often use the analogy of a balloon. Imagine tiny dots drawn on the surface of a balloon. As the balloon is inflated, the dots move farther apart, not because they are moving on their own, but because the surface beneath them is stretching. The dots represent galaxies, and the balloon's surface represents space. There is no center point on the balloon surface from which everything is expanding. The entire surface expands everywhere at once. This is how space behaves on the largest scales. It grows and stretches, carrying galaxies with it. But unlike the balloon, the universe does not expand into something larger. The balloon sits in the air, but the universe's expansion has no surrounding space into which it grows. Space itself is all there is. When it expands, it simply creates more of itself. This is one of the hardest ideas to hold in the mind, because we are creatures who live in three-dimensional environments and rely on comparisons to things we can touch and see. To say that time began is to challenge our most basic assumptions about reality. To say that space began is to confront the mystery of how nothing became something, yet physics, with its equations and observations, consistently points back to this origin. The cosmic background radiation, the expansion of galaxies, the proportions of light elements, all of these lines of evidence converge on a single picture. Time and space themselves had a birth. Einstein's theory of general relativity deepens this picture. According to relativity, space and time are not separate entities, but part of a single fabric called spacetime. Mass and energy bend this fabric, causing the phenomenon we experience as gravity. When cosmologists trace the equations of relativity backward, the fabric of spacetime itself shrinks, contracts, and ultimately seems to vanish at the Big Bang. This is the singularity, the point at which density becomes infinite and the known laws of physics break down. It is here, at this boundary, that the question of beginnings presses most sharply against the limits of human understanding. Yet even as science describes this beginning, it does not do so in isolation from wonder. To think that time itself has an age, that the seconds ticking away right now trace their lineage back to a moment of origin, is a thought that places us inside a cosmic story larger than any myth or legend. It suggests that we are not drifting in a timeless ocean, but rather flowing along a river with a source, a river that began with the birth of the universe. That river has carried us through the formation of galaxies, the ignition of stars, the birth of planets, and finally, to the emergence of life capable of pondering the river itself. But with this understanding also comes new questions. If time and space began, what mechanism or condition brought them into being? Some physicists suggest that quantum fluctuations, tiny bursts of energy arising from uncertainty, may have triggered the birth of spacetime. Others propose that the Big Bang may not have been the absolute beginning, but rather the transition from a previous cycle of contraction. In these models, time might not be a straight line with a single beginning, but a loop or a rhythm, endlessly repeating. Still others turn to the possibility of a multiverse, where our universe is just one bubble among countless others, each with its own version of time and space, each beginning with its own burst of creation. These are hypotheses, bold attempts to reach past the singularity, but they remain speculative. What we know with greater confidence is that the time you measure on a watch, the space you move through when you take a step, the distance you see when you look at the stars, all of these are part of a fabric that had an origin. The everyday experiences that feel most familiar are, in fact, connected to an event that defies ordinary comprehension. The ticking of a clock is a continuation of a process that began 13.8 billion years ago. The vastness of the night sky is a continuation of an expansion that started when space itself was born. In this way, the birth of time and space is not just a scientific concept. It is an intimate part of our lives, woven into every breath we take and every thought we have. It tells us that the ordinary is inseparable from the extraordinary, that the seconds we live are part of the same fabric that unfolded in the first instant of the cosmos. And as we lie back and let our minds drift into that vast beginning, we are reminded that even time itself has a story. And that story includes us. The quantum mystery before the Big Bang gives us a powerful story of beginnings. But like all stories, it leaves us wondering about the pages that might have come before. If the universe began with a singularity, if time and space unfolded from a point of unimaginable density and energy, then we must ask, what, if anything, existed before that instant? Was there a time before time? Was there a place before space? Or is our very language, our words, before and place, misleading us, because they rely on concepts that did not yet exist? Here, at the edge of understanding, the story of the cosmos turns deeply mysterious, and the questions lead us into the strange and uncertain world of quantum physics. Quantum physics is the study of the very small, of particles so tiny that they behave in ways completely alien to our everyday experience. In this domain, certainty gives way to probability. Particles are not always in one place at one time, but exist in a haze of possibilities. Events do not always unfold in neat chains of cause and effect, but sometimes appear to occur without clear reason. governed by chance and fluctuation. This is a world where the fabric of reality shimmers with unpredictability, and it is here that many scientists turn when they try to imagine what might have existed before the Big Bang. One idea is that the singularity itself was not truly a beginning, but the result of quantum fluctuations. Fluctuations are temporary changes in energy that occur even in what we call a vacuum. In quantum physics, empty space is never truly empty. It is filled with restless energy, with particles flickering in and out of existence for the briefest instants. Perhaps our universe was born from such a fluctuation, a quantum event that produced the hot, dense state we call the Big Bang. In this view, the birth of the universe was not a unique miracle, but part of the natural behavior of quantum reality. The cosmos might be the ultimate expression of quantum chance. Another idea is that of the multiverse. If quantum physics allows fluctuations to generate entire universes, then perhaps ours is not the only one. Perhaps what we call the universe is simply one bubble in a vast cosmic foam, with countless other bubbles forming and drifting, each with its own laws of physics, its own time, its own space. Some may collapse quickly, never forming stars or galaxies. Others may expand and last, as ours has. In this vision, the Big Bang was not the beginning of everything, but the local beginning of our particular universe. Beyond the edges of what we can see, beyond even the reach of our imagination, there may be other universes, other beginnings, other stories. Still another proposal is the idea of a cyclic universe. Instead of beginning once, expanding forever, and fading into heat death, the universe may be engaged in an endless cycle of birth, expansion, collapse, and rebirth. In this model, the Big Bang we know was not the first, but one of countless bangs that have echoed through eternity. The universe could contract under gravity, compress back into a dense state, and then rebound into expansion once more. Time, in this scenario, would stretch back infinitely, not in a straight line, but in a rhythm like a heartbeat. The Big Bang would not be the beginning, but just the latest pulse of an infinite cycle. What makes these ideas both fascinating and frustrating is that they push us beyond what current observation can confirm. The light we see, the signals we detect, can only carry information from within our observable universe. Anything before the Big Bang, or outside the boundaries of our cosmic horizon, is hidden from us by the very structure of spacetime. We cannot peer back before time itself began, because time is the medium through which we observe. We cannot look outside our universe, because space is the canvas on which all observation takes place. Yet science, with its equations and imagination, can still explore possibilities, sketching models of what might exist beyond the curtain. And in these models, quantum mechanics plays the starring role. At the smallest scales, spacetime itself may not be smooth and continuous, but frothy and uncertain. Tiny fluctuations could ripple through this quantum foam, creating pockets where spacetime briefly appears, then vanishes. If one of those pockets achieved stability, if its energy density was just right, it could blossom into an entire universe. Our universe, what we call the Big Bang, could have been that moment of blossoming, the instant when a quantum seed grew into the vast cosmos we inhabit. There is a strangeness to this thought, because it challenges the boundary between nothing and something. If quantum fluctuations can give rise to universes, then perhaps nothingness is never truly nothing. Perhaps what we call nothing is itself a seething field of potential, a womb of possibility, out of which existence can emerge. This is not the empty void of imagination, but a restless, fertile nothing, one that contains the rules of physics waiting to unfold. In this way, the universe may not need an external cause, because the capacity for birth is written into the very structure of reality. Of course, these ideas are not without controversy. Some physicists caution that we should be careful not to let imagination race too far beyond evidence. Others point out that the singularity remains an unresolved problem, a place where our theories break down. What we call the before the Big Bang may be forever beyond our reach, not because it does not exist, but because our tools for measuring and observing are bound within the universe itself. To ask what came before the Big Bang may be to ask a question nature does not allow us to answer. Yet even in the face of uncertainty, the question has value, because it pushes us to the limits of thought, to the edges of what science and philosophy can touch. For those lying awake at night, letting the mind drift among stars and galaxies, there is something deeply calming about these mysteries. To know that the universe itself might be one among many, or that time itself might cycle endlessly, is to feel both small and vast at once. Small, because our lives are fleeting compared to cosmic scales. Vast, because we are made of the same matter, governed by the same laws, as the universe itself. The quantum mysteries before the Bang remind us that existence is not simple, not straightforward, but filled with depths we can only begin to explore. And in that exploration lies a quiet wonder. Every breath you take, every thought you have, is carried out on the stage of spacetime, a stage that may itself have flickered into being from quantum uncertainty. The mystery of before the Bang may never be solved completely, but it deepens our sense of awe, and it ties us to the restless, fertile fabric of reality itself. When scientists first began to piece together the story of the Big Bang, the evidence seemed compelling. The universe was expanding, galaxies were rushing apart, and the cosmic background radiation filled the sky as a fossil of the universe's hot and dense beginning. Yet as powerful as this picture was, it carried with it puzzles that the Big Bang alone could not explain. Why was the cosmic background radiation so uniform across the sky, even in regions of space that should never have had time to communicate? Why was the geometry of the universe so precisely balanced, neither curving wildly inward nor outward? And why do we not see strange relics like magnetic monopoles that some versions of physics predicted should exist if the universe had simply expanded from a singularity without any additional process? These questions demanded answers, and in the early 1980s, a new idea emerged: cosmic inflation. Cosmic inflation is the notion that, in the first tiny fraction of a second after the Big Bang, the universe underwent a period of unbelievably rapid expansion, faster than anything we normally associate with the speed of light. This was not matter rushing through space, but space itself, stretching at an exponential rate. In less than a trillionth of a second, the universe may have grown from smaller than an atom to something much larger than a galaxy. This sudden ballooning smoothed out irregularities, stretched space into near-perfect flatness, and set the stage for the more gradual expansion that followed. Inflation was like a deep breath of the cosmos, a swift and silent surge that reshaped everything. To grasp the scale of this idea, imagine you are looking at a wrinkled piece of fabric. If you tug on it slightly, the wrinkles remain, though perhaps spread out a little. But if you pull on it with overwhelming force, those wrinkles flatten until the surface becomes almost perfectly smooth. Inflation worked in a similar way on the fabric of spacetime. Any initial curvature, any unevenness in temperature or density, would have been stretched to such an extent that the universe we see today looks astonishingly flat and uniform. When we observe the cosmic background radiation and find that its temperature differs by no more than 1 part in 100,000 across the entire sky, inflation provides a natural explanation. Another puzzle solved by inflation is the horizon problem. In the standard Big Bang model, regions of space that are now billions of light years apart should not have been able to exchange information or energy. Light simply would not have had time to travel from one region to another to equalize temperatures. Yet the cosmic microwave background shows that these regions do, in fact, have nearly identical temperatures. Inflation resolves this by suggesting that, before the inflationary burst, the entire observable universe was once small enough for different regions to interact and reach equilibrium. When inflation stretched space, those once connected regions were carried far apart, giving the illusion of separation while still carrying the same balanced temperature. The flatness problem also finds resolution in inflation. General relativity allows for universes that are curved, either positively like the surface of a sphere or negatively like a saddle. A perfectly flat universe, balanced between these two extremes, would require exquisitely precise initial conditions if it were simply expanding under the Big Bang. But inflation drives the universe toward flatness, regardless of its initial curvature. Just as inflating a balloon makes a small patch of it look flatter and flatter, cosmic inflation stretched space to such an extent that any curvature became imperceptible on the scale we can observe. Perhaps one of the most fascinating predictions of inflation is that it did not erase all irregularities. Quantum fluctuations, the tiny uncertainties that rule the microscopic world, would have been magnified during inflation. These fluctuations, originally on scales smaller than atoms, were stretched across cosmic distances. As inflation ended and the universe cooled, these ripples in density became the seeds of structure. Regions that were slightly denser pulled in more matter under gravity, eventually forming galaxies, stars, and planets. In this way, the immense beauty and complexity of the universe, the Milky Way's spiral arms, the clusters of galaxies stretching like cosmic webs, owe their origin to the whisper of quantum fluctuations amplified by inflation. The mechanism behind inflation lies in the behavior of fields, specifically a hypothetical energy field sometimes called the inflaton. During inflation, this field would have stored enormous amounts of energy, fueling the rapid expansion of space. Eventually, the field decayed, releasing its energy into particles and radiation, heating the universe in what is called the reheating phase. This provided the conditions necessary for the familiar processes of the Big Bang to proceed: nucleosynthesis, the formation of hydrogen and helium, and later, the formation of stars and galaxies. Inflation, in this picture, is not separate from the Big Bang, but an essential chapter at its very beginning, setting the initial conditions that made everything else possible. Evidence for inflation does not come from direct observation of the inflationary moment. It is far too early in the universe's history for that, but from the patterns it left behind. The tiny fluctuations seen in the cosmic microwave background, mapped with exquisite precision by satellites like COBE, WMUP, and Planck, match the statistical fingerprints predicted by inflationary theory. The large-scale structure of galaxies across billions of light-years also aligns with the idea that quantum ripples, stretched by inflation, grew into the cosmic web. Scientists continue to search for even more direct signs, such as a particular pattern in the polarization of the cosmic microwave background called B-modes, which would indicate gravitational waves produced during inflation. Detecting such a signal would provide extraordinary confirmation of this cosmic breath. Inflation also opens the door to ideas even stranger than itself. Some versions of inflationary theory suggest that inflation may not have ended everywhere at once. Instead, while our region of the universe stopped inflating and settled into the Big Bang expansion, we know other regions may still be inflating, spawning bubble universes within a vast multiverse. In this view, our universe is just one patch in an endless cosmic landscape, each bubble with its own laws of physics, its own history, its own fate. The Big Bang, then, was not the birth of all reality, but a local event in a far grander tapestry. As extraordinary as these ideas are, inflation is not without debate. The exact nature of the inflaton field remains unknown. Some physicists question whether inflation is the only or best explanation for the puzzles it solves. Alternatives, such as bouncing cosmologies or models involving modifications to gravity, continue to be explored. Yet inflation remains the most compelling and widely studied model because of how naturally it accounts for observations and how well its predictions align with data. For those who let their thoughts drift into the cosmos at night, inflation adds a new layer of wonder. It tells us that the smoothness of the sky, the balance of space, the very existence of galaxies, are all gifts of a fleeting moment of expansion, so brief, it is almost beyond imagination. In less than the blink of an eye, the universe swelled from subatomic scales to cosmic ones, carrying within it the seeds of everything that would ever exist. To imagine inflation is to imagine the universe taking a sudden and silent breath, a surge that shaped the stars, the earth beneath your feet, and even the atoms in your body. It is to imagine that the grandest structures of the cosmos were written into existence by the tiniest whispers of quantum fluctuations, magnified to cosmic scale by the stretching of space itself. For much of the 20th century, the picture of the cosmos was one of deceleration. The universe, after the Big Bang, was expanding outward, and gravity, the ever-present pull of matter, was expected to slow that expansion down. Astronomers imagined that over cosmic time, the expansion would gradually taper off. Perhaps it would come to a halt and reverse into a big crunch, collapsing back into a singularity. Or maybe it would continue forever, but at an ever-decreasing pace, asymptotically stretching out until galaxies drifted apart at a slower and slower rate. The universe was thought to be a tug-of-war between the initial explosive push of the Big Bang and the attractive pull of gravity from all the matter scattered across space. But then came one of the greatest surprises in modern cosmology. Instead of slowing down, the expansion of the universe was speeding up. This discovery came in the late 1990s, when two independent teams of astronomers set out to measure the fate of the cosmos using distant supernova as cosmic markers. These were not ordinary stars, but Type Ia supernova, the catastrophic explosions of white dwarf stars in binary systems. Because they all explode with nearly the same intrinsic brightness, they act like standard candles, allowing astronomers to measure distances across the universe with remarkable precision. By comparing the brightness of these supernovae with their redshifts, the stretching of their light as space itself expands, astronomers could trace the history of cosmic expansion. What they found was astonishing. The supernovae were dimmer than expected, meaning they were farther away than the standard model of a decelerating universe predicted. The only explanation was that the expansion of the universe was not slowing down at all, it was accelerating. To account for this cosmic acceleration, scientists invoke something that came to be known as dark energy. This mysterious form of energy, unlike anything we experience in everyday life, exerts a repulsive pressure on the fabric of spacetime itself, counteracting gravity and driving galaxies apart at ever-increasing speeds. Dark energy does not clump like matter, it does not emit or absorb light, and yet, it dominates the cosmos. Today, based on measurements from satellites and observatories, we estimate that about 68% of the total energy content of the universe is dark energy. Ordinary matter, the stuff of stars, planets, and people, makes up less than 5%. The rest is dark matter, an invisible form of matter that interacts through gravity, but not light. In this cosmic accounting, dark energy is by far the largest component, and yet, it is the least understood. One possible explanation for dark energy lies in an idea that dates back to Albert Einstein himself. When Einstein first applied his general theory of relativity to the universe as a whole, he realized that his equations implied a dynamic cosmos, one that should either expand or contract. At the time, however, the prevailing belief was that the universe was static. To preserve this picture, Einstein introduced a term into his equations called the cosmological constant, a kind of anti-gravity that could counterbalance matter and hold the universe steady. Later, when the expansion of the universe was discovered by Edwin Hubble, Einstein abandoned the cosmological constant, calling it his greatest blunder. Yet decades later, the idea was revived. Now, not as a mistake, but as a plausible description of dark energy. If the cosmological constant is real, then it represents the energy of empty space itself, a vacuum energy that pushes space to expand. The cosmological constant is simple and elegant, but it carries with it deep puzzles. Quantum field theory suggests that empty space should indeed have energy, arising from the constant fluctuations of virtual particles popping in and out of existence. But when physicists calculate the amount of vacuum energy predicted by quantum theory, the result is staggeringly larger by a factor of 10^120 than the tiny value needed to match observations. This is sometimes called the worst theoretical prediction in the history of physics. Why the vacuum energy should be so small, yet not zero, remains one of the great unsolved mysteries. It is as though the universe has chosen just the right amount of dark energy to accelerate expansion gently enough that galaxies, stars, and planets could still form, but not so violently that matter was torn apart before structure ever emerged. Other explanations for dark energy go beyond the cosmological constant. Some propose that dark energy is not constant at all, but dynamic, evolving over time. These models are sometimes called quintessence, after the ancient Greek concept of a fifth element beyond earth, water, air, and fire. Quintessence envisions dark energy as a field permeating space, with its density and pressure changing as the universe evolves. Depending on its properties, quintessence could cause acceleration to increase or decrease, shaping the fate of the cosmos in ways the cosmological constant cannot. Observations continue to test whether dark energy is truly constant or whether it changes with cosmic time. But so far, the data are consistent with Einstein's original cosmological constant. The implications of dark energy for the future of the universe are profound. If dark energy remains constant, the universe will continue to expand at an accelerating rate. Galaxies not bound together by gravity will drift beyond each other's horizons, becoming invisible as the light they emit can no longer reach us. Over trillions of years, the universe will grow dark and cold, with stars burning out and galaxies fading into the distance. This is sometimes called the heat death or big freeze. But if dark energy grows stronger with time, the acceleration could become so extreme that even atoms would eventually be torn apart in what cosmologists call the Big Rip. On the other hand, if dark energy diminishes or reverses, the universe could slow down again, perhaps even collapsing in a big crunch. Each scenario depends on the true nature of this enigmatic energy. To probe dark energy, astronomers have launched ambitious projects to map the expansion history of the universe with increasing precision. Large surveys of galaxies, measurements of the cosmic microwave background, and the study of baryon acoustic oscillations, the faint ripples from sound waves in the early universe, provide complementary ways of tracking cosmic expansion. Space telescopes like the European Space Agency's Euclid mission and NASA's upcoming Nancy Grace Roman Space Telescope are designed specifically to test dark energy by observing billions of galaxies across cosmic time. The goal is to determine whether dark energy behaves exactly like a cosmological constant or whether it reveals more complex behavior. Pointing toward new physics, the existence of dark energy challenges not only our understanding of the cosmos, but also our most fundamental theories of physics. General relativity, the framework Einstein gave us for understanding gravity, has been tested with exquisite accuracy on solar system and galactic scales. But the discovery of cosmic acceleration raises the possibility that relativity itself might need modification on the largest scales. Some alternative theories propose that what we interpret as dark energy is actually a sign that gravity behaves differently across cosmic distances. These ideas are speculative, but they highlight the depth of the mystery we face. Dark energy also stirs philosophical questions. Why does the universe contain just enough dark energy to allow galaxies, stars, and life itself to exist? In the vast landscape of possible values, most would either collapse the universe too quickly or tear it apart too violently for complexity to arise. This apparent fine-tuning has led some to speculate about the anthropic principle, that perhaps there are many universes, each with different values of dark energy, and we simply find ourselves in one where the conditions happen to permit our existence. This idea intersects with theories of cosmic inflation and the multiverse, suggesting that dark energy may not only shape the fate of our universe, but also hint at realities beyond our cosmic horizon. For those listening under the night sky, dark energy transforms the way we think about existence. It is not only a scientific concept, but a reminder of how much lies beyond our grasp. The stars we see, the galaxies shining across billions of light years, are part of a cosmos in motion, driven by a force we cannot touch or see. It is an invisible tide that carries everything outward, faster and faster, reshaping the future of reality itself. To contemplate dark energy is to realize that the universe is not merely expanding but accelerating into an unknown destiny, guided by something so strange that even the most advanced physics struggles to describe it. It reminds us that our story is part of a much larger one, across billions of years, and that the mystery of the accelerating cosmos is not just about distant galaxies, but about the ultimate fate of everything we know. When we look at the night sky, we see a vast universe stretching far beyond imagination. Billions of galaxies, each with billions of stars, span across cosmic distances so immense that light itself takes billions of years to cross them. Yet as immense and boundless as this universe seems, some scientists propose that what we call the universe may be just one bubble in an infinite ocean of universes. This idea is known as the multiverse hypothesis, and it takes our understanding of the Big Bang and stretches it to a scale that defies comprehension. Instead of the Big Bang being the beginning of everything, it may have been only the birth of our particular pocket of reality, with countless other bubbles born in ways similar or completely different. The multiverse hypothesis arises naturally from several lines of thought in modern physics, particularly from inflationary cosmology. As we explored in the concept of cosmic inflation, the early universe may have undergone a period of rapid expansion driven by a high-energy field. In many versions of inflation theory, this process does not stop everywhere at once. Instead, while inflation ends in some regions, allowing them to cool and form universes like ours, in other regions inflation continues indefinitely. This picture, called eternal inflation, suggests that space is constantly giving rise to new bubble universes. Each bubble may have its own Big Bang, its own expansion, and its own physical laws. We happen to live in one such bubble, but an infinite number of others may exist, forever beyond our reach. The idea of a multiverse does not stop with inflation. Quantum mechanics, the strange theory that governs the microscopic world, also gives rise to multiverse-like interpretations. In the many worlds interpretation of quantum physics, every quantum event with multiple possible outcomes actually plays out in different realities. When an electron could spin up or spin down, both happen, but in separate universes. If this interpretation is correct, then every choice, every random event, splits reality into countless parallel timelines. In one universe, a star collapses into a black hole. In another, it stabilizes. In one universe, you chose to listen to this very speech. In another, you chose something else. All these universes would coexist, though we could never interact with them. The multiverse hypothesis is sometimes criticized for being untestable, but it arises not from fantasy, but from serious attempts to solve real scientific problems. Consider, for example, the question of fine-tuning. Our universe appears to have physical constants like the strength of gravity, the charge of the electron, or the density of dark energy that are remarkably well suited for life. If gravity were slightly stronger, stars might collapse too quickly. If it were weaker, stars might never ignite. If dark energy were much larger, galaxies might never form. Why should the universe's constants take on such special values? One answer is that they are not special at all. If there are countless universes, each with different constants, then it is no surprise that we find ourselves in one where the values allow life. This reasoning, called the anthropic principle, does not prove the multiverse, but it makes it a compelling explanation for otherwise puzzling coincidences. Another route to the multiverse comes from string theory, a candidate for unifying all the forces of nature. String theory suggests that particles are not point-like dots but tiny vibrating strings, and the way these strings vibrate depends on the shape of extra dimensions curled up beyond our perception. The mathematics of string theory allows for an enormous number of possible configurations. Some estimates suggest 10,500 or more possible universes, each with different physical properties. This so-called landscape of string theory provides a natural backdrop for a multiverse, with each bubble universe realizing a different set of possibilities. Though the multiverse cannot be observed directly, scientists have speculated about indirect hints. For example, if our bubble universe ever collided with another bubble in the distant past, It might have left subtle imprints in the cosmic microwave background patterns or anomalies in the otherwise smooth radiation left over from the Big Bang. Some studies have searched for such signs, though so far none have been confirmed. Others look for ways that high-energy physics experiments, like those at the Large Hadron Collider, might reveal clues about the deeper structure of reality that points toward multiple universes. Philosophically, the multiverse challenges our deepest assumptions. For centuries, humanity has asked whether Earth is unique, whether the Sun is unique, whether our galaxy is unique. Time and again, science has shown us that we are not at the center of everything, but part of a much larger whole. The multiverse takes this principle to the extreme. Not only are we not at the center of the universe, but our universe itself may be one among countless others. This humbling perspective stretches the limits of imagination, forcing us to ask what it even means to talk about everything if our everything is just a drop in an infinite sea. The multiverse also raises questions about testability in science. Some argue that if other universes are forever beyond observation, then the hypothesis cannot truly be scientific. Others counter that if the multiverse arises as a natural consequence of well-tested theories like inflation or quantum mechanics, then it should be taken seriously, even if direct observation is impossible. After all, black holes were once considered unobservable, yet their effects on nearby stars and light eventually proved their reality. Similarly, the multiverse may be forever hidden, but if its existence provides the best explanation for what we do observe, it could still be a valid scientific conclusion. There are also variations in how the multiverse might be structured. In the inflationary version, each bubble universe might be completely separate, with its own spacetime. In the many worlds version, universes may exist in parallel, branching with every quantum event. In the string theory landscape, universes may occupy different regions of a vast higher dimensional space. Some cosmologists even suggest that time itself might be part of the multiverse, with different universes experiencing different flows of time or entirely different temporal structures. The diversity of possibilities underscores how little we truly understand about the ultimate nature of reality. For the listener in the quiet of the night, drifting into rest, the multiverse is a reminder that the universe we know may not be the whole story. Our Big Bang may have been just one note in an endless symphony, our galaxies, one constellation in a boundless mosaic of realities. The stars we see overhead may be reflections of deeper truths, where countless skies shine in countless ways, unseen, but not unimaginable. The multiverse, whether real or not, expands our vision of what existence could be, offering both wonder and humility as we contemplate our place in the grandest possible picture of reality. The story of the Big Bang has always been more than a tale of physics. It is also a story about meaning, existence, and the ways humans attempt to grasp truths far larger than themselves. When scientists first described the universe as expanding, it was not only a shift in astronomy, but a revolution in how people thought about beginnings. For centuries, many believed the cosmos was eternal and unchanging, stretching infinitely in all directions and persisting forever without birth or death. The Big Bang shattered that assumption, suggesting instead that the universe had a finite origin, a moment of creation from which everything we see today emerged. With that claim came both wonder and unease, because when you suggest a beginning, you inevitably invite questions about causes, purposes, and what might lie beyond. Philosophically, the Big Bang is often framed as the ultimate why question. If time, space, and matter began in that singular event, then what existed before? The problem is that before may not even be meaningful, because time itself was born with the Big Bang. Asking what came before time is like asking what lies north of the North Pole. It may simply be a question without a coherent answer. Yet human curiosity resists boundaries. Many turn to metaphysics, religion, or speculation about multiverses to provide frameworks where science cannot yet tread. Others see the Big Bang as reinforcing the beauty of natural law, where the unfolding of complex structure from simplicity acquires no external cause beyond the principles of physics. the philosophical implications also touch on human identity. If the universe had a beginning, and if it evolves under laws of physics, then life itself is not an accident of a static cosmos, but a consequence of cosmic history. Every atom in our bodies was forged in stars, but those stars themselves arose because the Big Bang set the universe expanding, cooling, and clustering into galaxies. In this sense, the Big Bang is not a distant abstraction, but the first chapter of our own personal story. The cosmic microwave background is the faint afterglow of conditions that eventually made our existence possible. This realization collapses the boundary between cosmology and meaning. The universe's birth is inseparable from our own. From a scientific standpoint, the Big Bang remains the most powerful model for explaining the cosmos, but it also highlights the limits of science. The further we push toward the beginning, the more our equations break down. General relativity describes gravity on cosmic scales with astonishing accuracy, and quantum mechanics governs the subatomic world with equal success. Yet when we try to apply them together to the singularity of the Big Bang, the mathematics collapses into infinities. This failure exposes a profound gap in our understanding. It suggests that a deeper theory, perhaps a theory of quantum gravity, is needed to unify the laws of the very large and the very small. Until such a theory is developed, the first fraction of a second after the Big Bang remains hidden behind a veil of mystery. This limit has significant implications. Science thrives on testable predictions, on experiments that confirm or falsify theories. But the moment of the Big Bang, by its nature, may be forever beyond direct observation. We can see the afterglow in the cosmic microwave background. We can measure the expansion of galaxies. We can infer conditions of the early universe through particle accelerators and theoretical models. But the singularity itself may be inaccessible. Some philosophers of science argue that this boundary challenges the very definition of science, forcing us to ask whether cosmology is a science like chemistry and biology, or something that straddles the border between physics and metaphysics. Others argue that science must stretch its boundaries, developing probabilistic or indirect methods for probing the unobservable. The implications also spill into debates about determinism and chance. If the universe emerged from a singularity, was it inevitable that it would evolve as it has? Were the laws of physics themselves born in that moment? Or did they pre-exist the Big Bang, governing its unfolding? Some physicists argue that the laws of nature are timeless truths, while others suggest they may be emergent, like rules that crystallized out of the chaos of creation. If the multiverse exists, then perhaps the laws of our universe are just one realization among countless possibilities, raising questions about contingency versus necessity. This tension between inevitability and randomness echoes through philosophy, religion, and science alike, showing how cosmology intersects with human attempts to understand order and meaning on a cultural level. The Big Bang has changed the language of existence. Before it, creation myths were dominated by deities, eternal matter, or cycles of death and rebirth. After it, even those who do not believe in divine creation must wrestle with the fact that the universe itself seems to have a starting point. This has inspired dialogue between science and religion, sometimes in conflict, sometimes in harmony. Some see the Big Bang as compatible with theological notions of creation ex nihilo, creation from nothing. Others argue that science strips away the need for metaphysical explanations, presenting a self-contained account of origins. The philosophical implications depend not only on the data, but on how individuals interpret the meaning of beginnings. The scientific implications ripple forward into humanity's future. Understanding the Big Bang is not just about where we came from, but also about where we are going. If the expansion of the universe is accelerating due to dark energy, then the cosmos may expand forever, galaxies drifting away until only cold emptiness remains. If dark energy changes or reverses, the universe might collapse in a big crunch or tear itself apart in a big rip. Each possibility redefines our sense of cosmic destiny. The Big Bang is therefore not only a past event, but also the key to predicting the future, and by extension, to understanding the lifespan of everything we know, ethically. These implications shape how we see our place in the cosmos. If the universe is finite in time, if it had a birth and will one day have an end, then everything we do occurs within a fleeting cosmic moment. Some interpret this as reason for despair, seeing our lives as insignificant against the vast backdrop of time and space. Others see it as a call to urgency, a reason to value every moment, to cherish existence because it is finite. The Big Bang thus becomes not only a scientific theory, but also a lens through which humanity views itself, its responsibilities, and its meaning. In the context of American audiences, these implications resonate strongly with traditions of both scientific curiosity and philosophical reflection. The United States has been at the forefront of cosmology, from Edwin Hubble's discovery of the expanding universe to the work of NASA's missions that mapped the cosmic microwave background. Yet it is also a culture steeped in debates about science and faith, determinism and free will, progress and humility. The Big Bang speaks to all these themes at once. It is a story of discovery and mystery, of equations and meaning, of a universe vast enough to humble us and intricate enough to invite endless exploration. The philosophical and scientific implications of the Big Bang remind us that knowledge is never complete. Every answer opens new questions. Every discovery expands the horizon of mystery. We may never know what, if anything, lies beyond the singularity. We may never observe the multiverse or resolve the puzzle of dark energy. But the pursuit itself, the act of asking, defines what it means to be human. The Big Bang, whether seen as the beginning of everything or only the beginning of our observable universe, is a story that anchors science in wonder and binds philosophy to the starsis. We draw this journey to a close. We return to the question at the heart of it all. Was the Big Bang really the start of everything? Science gives us a remarkable picture of a universe that began in fire and light, expanded across billions of years, and continues to accelerate into the unknown. We've traced the evidence written in the cosmic microwave background, the formation of galaxies, the strange dominance of dark energy, and the profound possibilities suggested by inflation and the multiverse. At every step, we've seen how the Big Bang is not just a single event frozen in time, but a gateway to questions that reach across physics, philosophy, and human meaning. For some, the Big Bang is the ultimate beginning, the birth of space and time themselves. For others, it may be only one chapter in a larger cosmic story, with inflation, dark energy, or the multiverse hinting at realities beyond what we can observe. What remains clear is that the Big Bang is not only about astronomy, it's about identity, destiny, and perspective. It tells us that everything we are and everything we see is tied to a moment of unimaginable transformation. It invites us to reflect on our fleeting place in cosmic history, not as insignificant, but as participants in a universe still unfolding its mysteries. So whether the Big Bang was the absolute beginning or simply the beginning of what we can measure, it stands as a reminder of the profound link between the cosmos and ourselves. It challenges us to remain curious, to embrace wonder, and to live with both humility and awe in the face of a universe far larger than imagination.